our afternoon session. We are basically following the program as it is written, but before starting, Monique is going to present to show you the portal, IPON portal. See? Okay, so just 5 minutes, and then we will continue with the program as it is written.
Okay, I'm stealing just 5 minutes of your time because some people came to me and asked for some practical information on how it works for the application to access the research infrastructures. So it's quite easy, I would say. You have to go on the Hyperion website, which is hyperionch.eu, and then you find access to facility, where you have the call for proposal and the description of all the three platforms that you will hear now in details: ArcLab, Fixed Lab, and Mahlab. So here you have the description of how it works. And then again, you have specific access to the three platforms, where you find the description of the single facilities, and in this case is ArcLab, so it's archives, and what each facility is providing in terms of access. So to what type of support for your research you will have access. So you have the same for ArcLab, for Mahlab, and for Fixed Lab, for instance. So here you have the description of the technique that you can access. So you can make up your request of access also by checking the facilities and the technique that are available. And then you just go to the call for proposal page, where you find, Okay, so in the call for proposal page, you will find detailed information on how the evaluation goes. It's a peer review process. And you also find the information on the calls and deadlines. So you see for ArcLab and Mahlab, we have 2 cutoff dates per year, 15th of February and 15th of September, while for Fixed Lab, there are different deadlines. So if you go inside the page, you will find information on the deadlines. And then, of course, you can download the application form, which is quite simple, I would say. It's different from platform to platform. And here you see you have the email address, because each platform has a kind of a welcome desk and a welcome officer, so you can address to him or her to ask for more information even before the application, to check and to pre-check the content and the relevance of your application, so you will also find support and advice. So this is for instance, for ArcLab. You fill in the application with some details of your research, details of your proposal, and some information about your background, your profile, and the reason why you're asking for access. It's quite simple, as you can see. And what is also interesting to me is that you can make also application to multiple facilities. So you can have access to ArcLab and Mahlab, ArcLab and Fixed Lab, or to different platforms within ArcLab or within Fixed Lab. So it really depends on you. As I said, we put a lot of information, or we try to put a lot of information in the web page. But again, if you have questions for each platform, again, there are some persons that are there to provide you with all information that you might need. And of course, you can always contact the coordination office, and we'll be more than happy to support you in this process. So I think that's it. If you have questions, I'm around anyway. Thank you.
Thank you, Monique. Okay, thank you, Monique. It is, I think it is, you will find all the information there, and we have seen how to access the facilities, and now we are going to see in this afternoon some details of these facilities and the specificities of the different platforms. We are going to start this session with the presentation of the Fixed Labs, the Fixed Laboratories, belonging to our Mexican colleagues, and we will start with 3 presentations from Ana Maria Soler. I will introduce both 3 at the same time, and then you can take the place. Ana María Soler, Alejandro Mitriani and Corina Solis, who will speak about their laboratories, the service offered.
Hello. Then I'm going to talk about the National Electromagnetic Service. Okay, then the National Archaeomagnetic Service is located in Morelia, Michoacán. It's like 300 kilometers from Mexico City, and the UNAM have a camp that is with like 6 or 7 buildings of different institutes of the UNAM, and it has a school. That one of the careers is the earth science, and it's a project. This lab is very well equipped because we obtain the support of the CONACYT, and I can say that, like I visit many laboratories, this is one of the most equipped in the world. And the method that we employ is for date. In my case, I date the floors where they were made with the stucco, or paintings too, and ceramics. And then we employ the Earth's magnetic field and the variation with the time to get the data. And this we have to develop many curves, the master curves of any one of the parameters of the Earth's magnetic field, 2 angles and 1 intensity. And for example, I think that for Mexico we need 3 different curves because it's very important the tectonic limits of the blocks. And then that is the reason that it's very different, the north of the country and the south, and specifically the Yucatan Peninsula is different because it's another body different from the North American block. And as you can see, it's very different. For example, in Europe, you develop a lot of different curves, very well precise, but the problem is that it's not useful for us. We have to develop our own curves of change. This is a curve for the intensity, and we employ also the volcanic rocks for the recent times. I can tell you that, for example, we are on the lava of a Chitle volcano that is only 2,000 years old, then very young for geological terms. And that is the way that we take the samples. We can take blocks or small specimens with the help of good cylinders. All has to be oriented with magnetic or solar compass, or for example in pictures, when the red is made with hematite, grinded hematite, we can obtain good dates too. Or the ceramics, the small fragments, this is another way to data, but only one parameter, that is the intensity of the field. These are the installations. They're growing because we begin with a small ¿cómo se dice? Las cabañas, cabin. And now we have two, and now a building, a complete building is growing to allow to have all the equipment. These are the change of the personnel. Many of them are students. We have magnetometers, susceptibilimeters, forms, the magnetizers, very good check equipment, really good. And for example, in this case, the shields, this is very expensive equipment, but we have it too. Or in this case, to study, to identify the materials in which material is record the magnetization. It's important. You can do many changes so to know if this ceramic has to be reheat many times or things like this. This is important for us to know. And this is another equipment that to get the susceptibility is important to identify the sources of the materials. And we write a book about the state of art, and many of the other authors, we are 3 Mexican authors and 3, 1 Spanish, 1 German, and 1 Greek, that we were working since many times ago. And then I show you the names of the many laboratories that we are working in archaeomagnetism in Europe. We have a good net to collaborate, and only I can tell that we only don't have one instrument that is a cryogenic magnetometer. Is the only one that we don't have, but for example, Burgos have one and Barcelona one, and in some cases we use the installations of them to get the results. Thank you very much.
So I'm going to talk about the Fixed Laboratories, one that we have here in the Physics Institute that belongs to the LANSIC, to the National Laboratory. And this is for ion beam analysis. We have a Pelletron accelerator, a 3 megavolt Pelletron accelerator. And this accelerator was established in 1995, and it has 2 ion sources. One for gases, which mainly for ion beam analysis we use alpha particles, and one for solid particles, which in general for analysis we use protons. From there, the largest energies, the highest energies we can use are 9 mega electron volt alpha particles and 4 megavolts for protons. We could go for 6 megavolt protons, but we don't have the radiation safety for it, so we limit it to 4 MeV. And in this laboratory we have 4 different research lines, but only 2 of them are for analytical composition, for analysis. One of them is the external beam line to your right, where we can do analysis on atmosphere pressure, and the second one is a nuclear microprobe beam line. The external beam line, we have a germanium detector. We have a setup with 2 X-ray detectors for PIXA, and solid particle detector for RBS analysis, Rutherford backscattering, and also a spectrometer for ion beam-induced luminescence or ionoluminescence. With this setup, and we also have our high-energy detector. It's a germanium detector that allows us to do gamma ray analysis, which is PIGE. With all of this setup, we can do analysis from light elements, fluor, sodium, all the way up to the whole periodic table. And well, with RBS, we can also characterize oxygen and lighter elements. And do also layer analysis. So we can do almost a whole periodic table. This is just to show the different analysis. And with ion beam induced luminescence, we can have mineral characterization and also characterize some impurities present in minerals and other luminescent materials like glasses. And well, some of the applications we have done over the years. We have a lot of lithic materials, the masks, and lots of counts, green stones. We have also done analysis on codex, on figurine statues, and well, lots of ceramics. Always a lot of ceramics. One of these examples, for example, is characterization of 19th century glass. And here, well, the characterization that allows us to see even parts per million in concentrations, allows us to see the colorants, decolorants, opacifiers, refiners, apart from the main components. And of interest, it would be the ionoluminescence, which gave some results giving different luminescent patterns, including the intrinsic defects and some impurities present in the different glasses. And well, then we have the ion microprobe, which was built based on an Oxford microbeam model using the triplet lens pattern with 3 quadruple lenses. And most of the design was following their own design, but the analysis chamber was designed in the Physics Institute, and it was built quite large compared to other analysis chamber or irradiation chambers, and it allows us to have 2 detectors for pixel, also to have a light element detector and a heavy element detector using an aluminum filter. And we can also mount a lens to capture the ionoluminescence light connected to a spectrometer, and a particle detector for RBS analysis. And well, we also have a microscope and a camera to visualize the area of analysis. Our beam spot size in this ion microprobe is 7 × 8 micrometers with a current of 100 picoamperes, which is sufficient to do almost all kinds of analysis. Some of the applications, well, the resolution is good enough to characterize painting layers in stratigraphic cuts, and also to do mineral analysis. Like here we have jade samples. And actually with these jade samples, we were trying to observe the composition, including trace elements, in just the matrix, the jade matrix. We really couldn't find any patterns, but we did find patterns on their luminescence emissions between the different samples analyzed. They did have some characteristic features. And well, just to sum up, to access this research facility, you have to send an application via email. This is evaluated by the scientific committee. And then the costs are divided between the user. Well, it depends on the arrangement. And the data interpretation is carried out at our laboratory, many times with input from the user also. And then we generate a report. So, thank you.
Well, before starting, I would like to thank the organizers, Dr. Rubalcaba and Dr. Barba, for the inviting me to talk a little bit about our laboratory. I am going to briefly tell you about our laboratory, what we do at the National Laboratory on Accelerator Mass Spectrometry, and the radiocarbon dating that we do in it. Here. ¿Dónde tengo que apuntar? Is here? Yes, perdón. Con la flecha. Okay, it's okay. Well, this is a briefly outline. I will tell you about the installation of the LEMA, as we call the laboratory, a little bit about the sample preparation, what we do for carbon-14 analysis, and I will talk a little bit about applications in archaeological studies and art and cultural heritage, and some conclusions. Well, our Accelerator Mass Spectrometry Lab opened in 2013 with support from the CONACYT and the university. It's a laboratory for research, teaching, and support for interdisciplinary projects. So you can see some pictures here of we have 3 laboratories for sample preparation. In the middle you can see the equipment. It's accelerator coupled to 2 mass spectrometers, and you can see also to the right the the carousel, and some of the pictures of open house, and some of the installation pictures that we took. Well, as I told you, it's a system of accelerator mass spectrometry with an accelerator 1 megavolt coupled to 2 mass spectrometers. And I list some of the research projects. We don't measure only carbon-14, but the main applications of the laboratory are carbon-14 applications, especially radiocarbon dating, and also radiocarbon as a tracer for environmental studies and also for forensic science. But we also measure some cosmogenic isotopes like beryllium-10 and aluminum-26 for environmental applications. And we plan to measure also, we are able to measure iodine-129 and the isotopes of plutonium. And we have, as you can see in the picture, a second line to the right, a second line for nuclear physics and instrumentation. Well, I guess many of you know the basis of the radiocarbon dating, but I will make a brief explanation. This technique started in 1946 with William F. Libby, who proposed to measure the time elapsed since the death of an organism by measuring the activity of the carbon-14 in the tissues. Then, because the carbon-14 is a radioactive isotope, when an organism dies, the carbon-14 decays, and the age can be determined by the amount, the remaining amount of carbon-14 in the rests. So you can see to the right the decay of the carbon-14 and the equation that allows you to determine the time elapsed after the death of the organism. So from this equation, we can then determine the radiocarbon age. some of the samples that we can measure at the laboratory are mainly organic samples, but also we can measure inorganic samples. Among the samples that we can date are, for example, hair, leather, bones, natural rubber, feathers, horns, charcoal, and also some soil organic matter, but we can also measure the carbon-14 from shells and from corals and other marine organisms. The procedure to measure the carbon-14 implies the separation of the CO2 and the graphitization of the carbon. So in order to measure the ratios of carbon-14 and carbon-12, or carbon-13 and carbon-12, we need then to extract the carbon and to convert it to graphite. So we need to make a pretreatment, a physical cleaning, and followed by a chemical cleaning. And then we have also automatized equipment for graphitization. And then once we have the carbon converted to graphite, we can do the analysis in the mass spectrometer. Then, briefly, the analysis of one sample of carbon-14 takes 4 samples of standards, 3 blanks, the samples of unknown age, and then the fraction of carbon, of modern carbon, is then calculated, and then the radiocarbon age is calculated also from this equation that I show you at the bottom. Here you can see the carousel. It has 50 samples can be analyzed in a single measurement. And in the bottom, you can see the cathodes that are introduced in each carousel. In order to measure carbon-14 or dating, we need to validate the methods. It's very important. So we have participated in several intercomparison experiments. We have made intercomparison with several laboratories in Zurich, with Direct AMS, with Beta Analytic, with Arizona, and also we have participated in international intercomparison exercises. Especially the last one was organized in 2014 by the Carbon-14 laboratory in Glasgow, in Scotland. And here I show you the results that were satisfactory. We also are a certified laboratory. Here I show you the last certificates that we obtained, one in 2017 and the more recent in 2018. I will tell you a little bit about some applications that we have done. Many people working in the archaeological sciences have come to our lab. And for example, I would like to talk about a very interesting study about the first humans in America. These samples come from the sinkholes in Yucatan, and cenotes from Quintana Roo. And the archaeologist is a subaquatic archaeologist, Carmen Rojas, who works in the National Institute of Anthropology and History. And also we have, for example, studies in pre-Columbian cultures. I will tell you about a project that we have in Teotihuacan. The timing and roots of the human migration to America is an important study, because we don't know if really the human arrived to the peninsula of Yucatan, and if they were when happened that, and also what kind of environment was at that time. Then there are some samples from skeleton recovered from Actung, and the dates that we have obtained are between 1,670 years and 9,525 before present, calibrated before present. And we can infer the age of the skeletons because of the level of the sea. The sea level has changed in the last 13 years, and several levels have been established. And then if archaeologists found a skeleton, for example, underneath the level marked by the geological data, then we can imagine that these bones are older than the sea level at that time. So we expect to find skeletons from older than 8,000 years. And to the right, I am showing you one cave with several points where fires were found. And these fires are supposed to be left by humans, and they were about 9,000 years old, or older than 8,000 years old. Another project very, very interesting that we are collaborating in is the Telecom Project. In 2005, scientists from the National Institute of Anthropology and History discovered a tunnel underneath the Temple of the Feathered Serpent at the Citadel in Teotihuacan. They have so far recovered more than 100,000 objects, and they brought us about 50 samples. And the objective of this study was to know when the tunnel was built, for how long they used it, and when was closed. So some of the samples that we analyzed are showed here. For example, rubber balls, animal bones, charcoal, and marine shells. So briefly, what we can say about the tunnel is that the pre-Citadel, where the tunnel is, may have been built since the 1st century of our era, and apparently the tunnel was used for more than 100 years. And before being torn down or closed for good, the tunnel was built maybe about in the 1st century. It was used for about 100 years, and then it was closed definitively around 530 years after Christ. This is a conclusion made by not only by radiocarbon dating, but also from other archaeological criteria. Well, also we have also made some analysis of a piece of art. The very first piece that we dated here in the lab was an Egyptian ibis. Believe it or not, it was our very first, an Egyptian ibis in Mexico, and it was older than 2,800 years. We also received some objects from museums. One was this beautiful piece of art in ivory. It's in a mammoth incisive, and we dated for more than 40,000 years. But the artwork was done in I guess in the century, a century ago. Well, in conclusion, then, briefly I can say that the research projects developed in LEMA are interdisciplinary with practical applications. AMS in Mexico is incipient, but offers great opportunities for interdisciplinary applications. And well, this is a great opportunity to consolidate LEMA as a tool to support research, mainly in the dating area of the historical and cultural heritage of Mexico, Latin American, and well, now that you are here, maybe in Europe and other countries. And thank you very much.
Okay, thank you very much. Thank you for presenting these 3 laboratories, and also thank you for doing it in a very brief time. I know it is difficult, and I appreciate that you have stick to the time. Okay, is there any? We are going to have some discussion at the end of the presentation, but if any of you have any specific question now or for one of the presenters, if not, I mean, we are going to have this at the end. Okay, if not, we are continuing with the European part of the Fixed Lab. Tibor Kuhn from the Budapest Neutron Center will present the access to large-scale facilities under Hyperion and NEEs. Tibor, thank you.
I think this. That I will sit down there.
Yeah.
Okay. Y esto es.
Esto debería ser, pero voy a ponerle.
Vamos a buscar aquí.
Sí, vamos a buscar primero aquí la.
Porque ya estaba, incluso ya estaba registrado aquí.
Sí.
Just a second. Sí, este. Yo lo voy a mover desde ahí, desde la silla.
Sí, perfecto. Debería funcionar. Me he conectado ahora. Okay. A ver si funciona.
Mira, ya tiene el micrófono y te lo hago.
Sí. Okay. Gracias.
Very huge scientific project between 2005 and 2009, steadily, continuously. We were fighting to create a new generation spallation source, its name is, in Europe. We were fighting among Spain, Hungary, and Sweden, and unfortunately for us, for the Hungarians, this huge new research reactor is being built in Sweden in the university town of Lund. So I am here for this moment to present for you the Fixed Lab facilities. Among them, the platform 1 will be the Hungarian Budapest Neutron Center. But first of all, we have to have a short introduction that the goal of Fixed Lab is to provide access for the cultural heritage community to large-scale facilities that develop and maintain sophisticated state-of-the-art instrumentation for advanced diagnostics and archaeometry. access is offered to researchers in heritage science to help address the major questions raised by the materiality of cultural heritage artifacts in terms of their genesis, manufacturing process, alterations, conservation, and preservation. But as a point, we have to emphasize also that Iberian cultural heritage is a consortium of 24 partners that aims establishing a unique European research infrastructure for restoration and conservation of the cultural heritage. At the same time, offers training, schools, and access to a wide range of high-level scientific instruments and techniques and methodologies. And Hyperion is part of IRIS, that is an SP proposal. So going on, the presentation of my task will be, first of all, the two Hungarian platforms. The first is Atomki, the second is Budapest Neutron Center. Both of them form part of that research infrastructure that belong to the Hungarian Academy of Sciences. And the Budapest Neutron Center is a consortium of the Center for Energy Research and the Wigner Research Center for Physics, both belonging to the Hungarian Academy of Science. And after these two Hungarian Fixed Lab research infrastructures, I will show some properties about the bigger one, which is under the Louvre, the Museum of Paris, Aglaé research infrastructure, and the fourth one will be the Soleil synchrotron infrastructure. So, the Hungarian Academy of Science has Atomki as an association with the University of Debrecen since 2000, in collaboration with several research institutions, universities, and museums in the region. Atomki has been actively engaged in cultural heritage investigation, applying elemental analysis and carbon dating for decades. Hyperion cultural heritage was managed by the Laboratory of Ion Beam Application, which provided approximately 1,200 hours of access within the Charisma project. As a recognition of the work carried out in the IBA lab, the 11th International Conference on Nuclear Microprobe Technology and Applications was held in 2008 in Debrecen, and training schools have also been organized here. Besides ion beam analysis, additional analytical techniques are also available at this Atomki research facility, such as scanning electron microscopy, AMS carbon 14th, X-ray fluorescence, SIMS, XPS, optical microscopy, etc. Atomki has developed an active presence in the field of cultural heritage research, participating in various technical cooperation and coordinated research, as well as cost action programs. Here are some buildings of that research infrastructure and some photos on the accelerator, and will be other slides among the most important facilities that you can find and you can reach and you can apply for as possible cooperating partners with these Hungarian institutions. They have scanning nuclear microsonda, they have accelerators, different accelerators, mass spectrometers, and they have an electron cyclotron resonantia ion beam source as well. Other instrumentation that are also available in the scientific instrumental park in 2018, as you can see, are these. They have the line, the nuclear microprobe, and they have also facility to do several kinds of very typical and proper measurement, either on lapis lazuli or gold leaf tesserae, or a decorative metal object, or gilded silver, as well as the pieces of potteries, what they analyzed already. Oops. So we turn for the Fixed Lab Hungarian platform B2, which is the Budapest Neutron Center. And this Fixed Lab takes advantage of the large-scale facility that offers the Budapest Research Reactor. All the participating laboratories are members of the Budapest Neutron Center, and they function as a consortium of research institutions of the Hungarian Academy of Science. At this point, I have to emphasize that next year it will be the 60th anniversary of existing of this Budapest reactor, research reactor, and that there is another good perspective about this reactor, that the international authorities as well as the Hungarian government gave permission for prolonging the lifetime from 2023 up till 10 years more. So it's secure that this research reactor will produce neutrons till 2033, which is a very important question in this sense in the region. The most attractive feature of the Budapest platform for non-destructive study of cultural heritage objects is the availability of a broad selection of neutron-based experimental techniques. As you probably know better than me, these are the prompt gamma activated analysis, the prompt gamma neutron-induced analysis, the neutron activated analysis, neutron radiography, time of flight, non-destructive, or the small angle neutron scattering, the SUNS instrument, in combination with complementary non-neutron methods. This can be, in our case, external beam PIX, XRF, and others, and on the same campus. So the above advantage has been confirmed by the significant overbooking of measurement days. Generally, our research reactor offers about 150, 165 days for cyclical functioning. Meanwhile, there are short periods of maintenance as well in between. So, these are some of the enumeration of the non-destructive methods available in our Fixed Lab in Budapest Neutron Center. And if we go further on, we can state that the Budapest Neutron Center offers its instruments to the national and international scientific user community through a peer-reviewed proposal system. Beam time applications are welcome in the following fields of research: structural analysis, inelastic neutron scattering, powder diffraction, high-resolution powder diffraction, small-angle neutron scattering, neutron activation analysis, prompt gamma activation analysis, Newton reflectory with polarization option, and neutron and X-ray imaging. The instruments offered in each call twice a year available on the website. All proposals are evaluated by the International User Selection Panel, assessing the feasibility, safety, and the potential for high-impact science. Hereby, I wanted to show some very important instruments, mentioning, for instance, that the neutron and X-ray radiography is able for two-dimensional and three-dimensional imaging with thermal neutrons and X-rays as well. Here is an illustrative external millibeam PIX application in archaeology that participated very strongly in the Charisma project in the previous of Epirian cultural heritage. So you can see and observe what were the main analysis and the person name from Poland, from Italy, from Germany, from Great Britain, Romania, Germany again, from Hungary, the two last trials, measurements, what have done there. This is quite a new instrument. It was built less than 10 years ago. It's a high-resolution time-of-flight diffractometer. And very important, the measurement possibilities on this instrument for minerals and for metals that come out from the archaeometrical and the cultural heritage investigations too. For instance, this is a Bronze Age defensive armor in Eastern Europe that was done in combination of several neutron, non-destructive, and non-neutron instrumentation that are all together in the same facility site. And of course, it was after the successful measurements, it was a almost obligated publication of the scientific newsletter. This is the other very much used neutron instrument, the small angle neutron scattering, that we call, because of its size and because of its color, we call the yellow submarine. So there can be seen that studies of defects, precipitates in materials, surfactants and colloid solutions, magnetic correlation, alloy segregation, and many more other type of trials can be done. This is a very demanded instrument among the 12 which are now offering, and we have other 3 neutron instruments that are now just modernizing, upgrading. So totally this platform, the Budapest Neutron Center, can offer from the next year 15 different instrumentation to work, to cooperate. This is prompt gamma activation analysis, where you can try all chemical elements, induced prompt and delayed gamma radiations, routine element analysis, and large sample prompt gamma activated analysis on this. And this is also very much combined with the NIPS norma and the neutron activated analysis for non-destructive, positive, position sensitive element analysis and neutron imaging with cold neutrons. This is another type of measurement that was done together with Hungarian researchers and foreigner researchers as well, and they're used for this sealed Egyptian pottery, the neutron imaging, and the PGA instruments. You can see that well-collimated neutron beam, local elemental composition of the mobile content was identified as organic material, presumably germinated seeds. What you can see on this photo on the right side. There was very important analysis done also on meteoritic origin of mankind's earliest iron artifacts in time of flight instrument combined with the prompt gamma activated analysis as well. I will go a little bit. Neutron radiography, there are 2 of the outstanding Hungarian physicians on this Center for Energy Research. They were measure these pieces, metal pieces, and all 3 artifacts have a central hole along their long axis, not visible during visual inspection due to their corrosion, but demonstrates that the beds were made from rolled iron sheet with areas of overlapping metal visible at the center of the seam. This would have required repeated hammering with intermittent annealing. Other very important trials and new insights about battlefield archaeology were done by this instrument, seen here. The study was the composition of a collection of lead musket balls recovered in 2 very different European battle sizes. One of them was nearby Moscow, the so-called Berezina battle, and the other battle was the Waterloo battle. Almost the principal star in these battles was Napoleon. And here you can see, as a highlight, the characterization of Napoleonic era artifacts uncovered at the Berezina battle site using neutron techniques, Duncan Atkins Institute in ELL in France. And they were comparing with those artifacts what were uncovered in Waterloo, near Brussels. Another highlight about the activities in the cultural heritage measurements, it was the organization last year in Budapest, the neutron imaging and neutron methods in archaeology and cultural heritage, with the cooperation of the International Atomic Energy Agency. It was located at the Academy of the Hungarian Academy of Science, and these were the sponsors of that event. I wanted to show this slide because the first line, they are the principal actors of this event. The second line, they are the most important first line sponsors, in between Hungarian National Museum, in between International Atomic Energy Agency or Elsevier. And the third line, you can see two startup industrial partners. One of them is Neutron, located near the Budapest Neutron facility, and Neutron Optics and other neutron guide and other instruments, detectors are made by this Hungarian industrial startup company, and the other one, Volume Graphics, it's a software company. And we were also sponsored at this occasion by two European big projects, Hyperion Cultural Heritage and the Brightness Project. So this is already changing of country. We are in France. We are 3 levels below of the Louvre Museum, and we can see in a completely renewed facility, because it was covered by the water of Seine 2 years ago, and French had to reorganize and rebuild the whole facility, and they have done in less than 1.5 years. These are the main detectors from different points of view, and here will appear the industrial company Thales that won the bid with the following proposal. What they were reconstructing here, the terminal voltage is controlled through a digital system directly integrated to industrial logic controller, and new devices for the alpha zone. These are the main elements. Other particle instruments with their details, physical details, other. So the new AGLE is with multi-detectors, with systematic imaging possibilities and beamline automation. This fourth big platform, stable research infrastructure, is also in France, is the Soleil synchrotron, where you can find on the left side some of the instrumentation, X-ray microtomography, photoemission spectroscopy, and additional support in sample preparation, complementary experiments in data processing. The leader of this big research infrastructure is Frederick Fressel. And they use 11 beamlines for cultural heritage related research. This is a quite impressive photo on the number of experts and employees who are working for this instrument, and most of them are involved in research heritage, in cultural heritage research. I wanted to express about this in between the 11 beamline. This is one of the most important because 70% beam time reserved for ancient materials. And the name of this instrument is PUMA, from the abbreviation of the French expression, photons utilisés pour les matériaux anciens. These are the characteristics of this PUMA instrument. This is another important aspect on this Soleil synchrotron infrastructure, the X-ray fluorescence that reveals that the distribution of manganesum in element known, in the first picture, to be incorporated in fossil bone during fossilization, and the second, to be involved in apatite ultraviolet luminescence, is restricted to a specific luminance color. So thank you for your kind attention, and these are the home pages if you want to, and of course you may have contacts and questions. By the way, I am also here for answering as many questions as you may have after this lecture or during the 2 days event. Thank you very much.
Thank you very much, Tibor, for this presentation of the Fixed Lab, of the different laboratories that are available under Hyperion. So again, if there's any specific question now for Tibor, if not, we will have time afterwards after the So we have finished with the fixed instruments, and now we are moving into the mobile instruments. We know that in many cases we cannot take the objects to the lab, so we have to take the lab to the objects. We are again, we are presenting first the Mexican facilities, and then we will continue with the European side. We will start now with the presentation by Luis Barba from the Institute of Anthropology, isn't it? Anthropological Research of the UNAM, and we'll continue later with Edgar Casanova from the Institute of Physics.
celeste si prefieres, o si aquí. Está muy bien. Ah, pero para pasar y el puntero está aquí. Sí, pero el micrófono. Mejor aquí. Sí, sí. Well, thank you. I'm going to be very concise and give you an idea of this mobile archaeological prospection laboratory. As you can imagine, especially the archaeological sites are things that we cannot take into our laboratories, so is by definition one of the mobile laboratories, and we have to move all our equipment to the archaeological sites. The methodology we use for this kind of research includes from large-scale satellite images to the sampling and chemical analysis of floors or soil samples to pass through different steps that produce different layers of information, and interpreting all them together, the idea is to reconstruct a three-dimensional space that includes the archaeological remains and have an idea of what kind of activities, of what was the purpose of the settlement, the human settlement there, the production area we are studying, or the dimension of the buried archaeological structure is over there. As I said, we start analyzing cartography, aerial photography, images from satellite, and we put all this previous information in a geographic information system. Then we approach the site and try to understand the geology, the geomorphology of the place we are going to work. And then with this previous information, we got into the archaeological site and make a survey and make the topography of the area, and sometimes with some drone we use to get the image of the area we are working or want to work on that. After these three steps, we have a very good idea of the distribution of materials, spots, topographic relief on the area, but we are not passing through the surface. We are on surface trying to get as much information as possible. Then we pass through the geophysical survey, including magnetic, electric, and electromagnetic properties, measuring them on the surface, but getting information below the surface. And finally, once we have an additional idea of the depth, of the dimension, of the characteristics of the buried structures, we had the chance to know a little bit about the stratigraphy, the layers, and to take samples to get some chemical information in addition to the previous one. And finally, we got an interpretation. This is the general idea of our work in the archaeological sites. Around 1983, we designed and built a mobile lab, a true mobile lab. We include in this all our geophysical equipment, but also our aerial balloon. We got a balloon on that time, and we got some simple chemical tests to work inside the laboratory. So that was a nice experience. And with that big balloon, we took our first photomosaic in 1985 in Teotihuacan. and we developed the films and make the impressions in the field during night every day. That was a nice experience, but the interesting thing is that from that time to the present, electronics has provided us with a very smaller equipments, digital cameras, don't need anymore the black room. So a big transformation in the technology available to work in the field. So we decided 10 years after the construction of the mobile lab that it was not necessary anymore. So we move in a small van with all the equipment now. One of this equipment is our differential GPS to make the topographic surveys, and it is also a very high resolution, and it is a very nice piece of equipment. After the optical equipment we began to use in the years previous to this technology. Also, the magnetic gradient is a very good tool for measuring the properties, the magnetic properties on surface, and to produce this kind of maps with the distribution of magnetic anomalies in the field we work. And sometimes like this, we can get also even the architectonic map. Also, when we use the magnetic gradient in conjunction with the electric resistivity, we produce some way of clarify difficult situations like this in Magdala, Israel, where it was so many volcanic stones on surface that it was really difficult to interpret the magnetic gradient map. So with the help of the resistivity map, we clarify a little bit better, and we had the chance to identify some structures, some linear patterns, some reticular patterns, and it was successful, the combination in this specific place. In addition to the previous geophysical techniques, we also have been using the radar, the georadar, it is very useful, especially in urban conditions. And in this specific case, it was very useful to try to make a diagnostic of the underground of the Hagia Sophia. It was because some instability of the whole building, that is it was the same phenomenon that here in Mexico City, that the differential sinking of some parts of the building, and at least for this specific case, there are remains probably from the Roman or even Hellenistic epoch under the present pavement, marble pavement, inside the main nave of the Hagia Sophia museum now. It was a very nice experience in a joint project with the University of Calabria. One of these interesting things is it was, I'm going back to let you know, in this specific part, it was an interesting anomaly that show us that there is a refill here with some very well-defined line, perhaps walls here, and characteristic reflection for some chamber, small chamber here in this part. So it was interesting. It has not been excavated yet, but there are so many things, interesting things under that floor that we want to go back and continue with this. Also, the chemical analysis that we used to take samples and take them to the lab, now it is possible to make it in the field, but we rather like to take the samples because there are so many opportunities to make chemical analysis and some other kind of analysis to complement the information. And the fact is that it is possible now to take all these pieces of equipment to the field and make also the chemical analysis and see the distribution of elements in the surface of one archaeological site. Well, that's it. I just want to say that this is one of the possibilities of taking equipments with you to the field, and the methodology we have been using for the last 30 years has been working fine. Thank you.
So we'll continue with our mobile lab here at the Physics Institute. I will go as fast as I can because I want to show you what do we have at some examples of what we have done so far. So I don't go through this. We all know why do we need to have a portable equipment, because it's already been said today. So let's go to what we have in the lab. This is a incomplete list of the spectrometers we have. We have a couple of X-ray fluorescence systems. One was developed at the lab, the other one is a commercial one. We use them depending on the case we're studying, depending on the need of portability of we are going to a cave or we're going to a museum. It depends on what we need to study. We have a couple of 3 infrared spectrometers, all portable. We have 5 Ramans with several wavelengths lasers, so that we can also use them depending on what we are going to study. We have another X-ray diffraction, a portable, even is our biggest portable equipment. Well, we have used it some 900 kilometers from here already, and have a simultaneous possibility to analyze X-ray diffraction and X-ray fluorescence on the same spot, on the same sample. We can use it on powder samples. We can use it on mural paintings, on flat surfaces. We can use it in almost in a wide range of objects. We are using very much lately the fiber optics reflectance spectroscopy because we have found that it's a very good method for a quick scan and to have some idea of what we are analyzing when it comes mainly to organic dyes. We also have a small non-contact colorimeter. They complement each other. We are working a lot on imaging, mainly in false color infrared imaging with a set of proper illumination and filters to have the visible and infrared information. We also have a couple of multispectral and hyperspectral image scanners, so we can go from visible to some part of the infrared interval. And we have also a portable digital X-ray imaging equipment. We also have a few more equipment, but these are the main ones that we use. We have traveled a lot through the country, so I guess most of this we do it by road. We pack everything. We take a van and we drive for 1 or 2 days. I guess the longest this was to Merida. It's about the distance from London to Rome, something like that. It takes 19 hours or 2 days. It depends on what we're using. We have covered mainly the center and southeast of the country, a couple of works in the north. And I go briefly to some examples of what we have done. This is a very interesting example because we were working together with an exhibition that took place last year, and it was based on the use of cochineal in modern art, in the arts. So they asked us, can you help us to identify cochineal in a fast and precise way? So we tried what we had and we decided to go for the force. And this is part of what we did only on textiles. And we studied a set of historical textiles here in Mexico City. And we were able to identify not only cochineal but also Brazil wool. It's another red dye that sometimes is difficult to differentiate. It was very easy with force because we have this black characteristic spectra. You will see now when we analyze this other one that was dyed with cochineal. It was a different spectra mainly because of these two bands there, and from the another spectral feature. I don't get to go into that detail. We were also able to find not only the presence of cochineal but also the presence of cochineal more dented with iron. So it tells us about the weight, the dyeing method in this case. And we also in this piece we found the presence of cochineal, of Brazil wood, and also the cochineal mixed with indigo for the dyeing. So this is a very powerful tool, and it's a very portable one. And from this is the numbers that we found. We couldn't identify the modern dyes because we don't have still yet the needed database, but it's just a matter of time and work that we have that too. Another example is something that we have done a lot in the last years is to study the greenstone offerings in the Mayan area, and this one was in Bonampak, but was from Bonampak. This is a site over here, and it was a burial that was beneath this impressive room, and this was part of the offering. We studied this offering and also some more offerings from the Bonampak sites and from other sites around Bonampak, and we use a combination of molecular and X-ray diffraction techniques and also X-ray fluorescence in order to try to find out something about the provenance. So with the infrared spectroscopy, we were able to identify the main minerals, and we identify a lot of them actually, and we could even identify a mix of jadeite and amphasite in some beds. With Raman, we confirmed some of these findings. We found that for this case, for greenstones, it's much better to use the 532 line of the laser, even though we could have some very good spectra with the red laser, but it's not so common. Usually you get only fluorescence. And when these two are not conclusive, we turn to the X-ray diffraction because it's better, because very precise, but it takes a longer time. So you can get the infrared and Raman results in about 30 seconds, but you need 15 to 30 minutes for each sample on the X-ray diffraction. So we set this kind of flow to only the difficult ones went for the X-ray diffraction to be sure. And then we're able to identify almost all of the mineral phases present on the samples. We found a very interesting concentration of amphasite plus jadeite and in the main boreal, and not so much a selection in the other offerings. And from the provenance, we know that in the Mesoamerican area we have only, well, no, so far we have found only two sources of jadeite that we have here in Guatemala. And we compare what we had for the elemental analysis, and we found that we have 4 groups. But the samples from here are grouped in this area, so we had 3 more sources, at least. In this offering, we don't know where are them from. We don't have enough information, even not geological information, about the jade sources, and there is a lot of work that needs to be done for the geological survey about this. I will go very fast from this. And the last example is one study we did in Chihuahua, in the northern part of the country. We went to study the colonial missions. We have about 300 colonial missions, all their remains in Chihuahua, and some of them have a lot of beautiful painting in the ceilings. So we had 5 days to cover 4 missions in the state, and we used the combination of force colors infrared imaging and force and XRF to get the molecular and elemental information. This is an example of what we got from the force colors infrared. So we were able to identify which areas of the painting in the ceiling are similar. And we also have an idea from the change in the color from this kind of blue to this kind of red, and from this also red to the yellow. For a previous analysis, we have an idea if there might be indigo, there might be iron-based reds and something like that. So from fluorescence, well, we know that we had a probably a gypsum background. It was calcium and sulfur everywhere. That we have iron in the reds and in some yellows. That we only in this case we have lead in these phases, and some copper in the blues. But we didn't have anything to tell us what was in this blue, because it was indigo. It was an organic dye that we identified by force, and it's very far away from the usual place where we can find indigo in the Mayan area. And we also find cochineal in these shaded red flowers. And all over there we found gypsum we confirmed the presence of gypsum with the force. And so it was a very nice study, because we were able to do a lot of work in a very short time, and we think that this combination of techniques can be applied into many other places in the country that needs to be studied in a non-destructive and in situ way. And how to work with us is about the same that Alejandro showed before. We receive application by email, we analyze them, and then we do the work either in our lab or in situ. And then we do the interpretation together with the user sometimes, and we give a report. And that's it. Thank you.
Okay, thank you. Thank you very much. We will continue now with the presentation of the mobile laboratories by Rafaela Fontana. She will present the mobile laboratories first, and then the Arc Lab, isn't it? Yeah, which is the third platform of Hyperion. The laser here. This laser, and this one to go front. Thank you so
much. So good afternoon, everybody, and thank you for inviting me. I will start by presenting the Mahlab at a European level. As it has already been told, the platform in the ongoing project Hyperion are ArcLab, DigiLab, and Fixed Lab. And in the new infrastructure, there will be also the Digilab platform. As it has already been said, why moving instruments to the artworks? Because generally speaking, artworks are very delicate and fragile, so a group of roaming scientists has decided to travel around Europe in order to measure artworks and perform non-invasive diagnostics. So our goal is to help others research by means of non-invasive techniques, either contact or non-contact techniques. And our instruments are mainly forefront tools for the analysis of cultural heritage, both chemical and physics devices. So, due to the uniqueness and preciousness of materials and artworks, our methods are non-invasive, and due to the difficulty of move the most part of artwork, we are moving to the artworks. These are the boxes that our scanner needs, for instance, to be moved all around Europe. And like the Mexican group, we also have a van for moving instruments. This is the van of the group from Perugia. And if you have, and these are boxes for the instruments of the group from Perugia. And sometimes it is very tough to move our instruments, such it was the case of measuring Pollock in Venice. I don't know if I am able to show you a very short movie in which we have to travel by car from Perugia and Florence to Venice, and then ship our instruments on a sort of boat, and then move the instruments from the boat to the museum. And it was very tough also for our back and so on. So, who are Mahlab providers? At the beginning, CNR, that is the Consiglio Nazionale delle Ricerche, the main national institution for the research in Italy, and then the CNRS, the Centre National de la Recherche Scientifique from France, and the last groups are from Forth, Greece, the Nicolaus Copernicus University from Poland, and Aachen University from Germany. Who are the Mahlab's users? They can be art historians, archaeologists, conservators, curators, or even scientists. Mahlab, in practice, we have 2 calls per year, and after the proposal preparation, and you can also benefit from a help desk for users. You have to submit your proposal, that it has to pass from a peer review panel, and after the decision, if selected, the project is scheduled and performed on site for free, obviously, for the users. At the end of the Mahlab access, the user is requested to produce a sort of experimental report as well as satisfaction report. And whenever the user publish something, he is kindly asked to also cite the Hyperion CH support from the European community. A little history of Mahlab evolution. It started during the EU Arctic project from 2004 to 2009. We were one provider, just CNR, with 12 equipments. And then during Charisma project, the equipments were 15 with 2 providers, Italy and France. And during the ongoing Hyperion project, we have 19 equipments, 5 providers that are Italy, France, Greece, Poland, and Germany. This is a map of our displacement around Europe during the 3 projects. So also we have traveled a lot all around Europe, and not only in Europe. And this is a list of our main instruments. The ones highlighted in blue were all developed in the framework of the European project Charisma, and now they are available in the Mahlab platform in Hyperion project. A bar plot of our KPIs, not to say that we are good, but simply to show that we have many requests, and our access provision efficiency was 74% at month 36, but we are supposed to make all our accesses by the end of the project. A few examples of success story, like Luca wants us to call them. So this was a measure at the Armada portrait of Elizabeth I in the Royal Museum in the UK. And the goal was to provide an insight into the paint layers, the technique used by the artist, and also on the conservation history of the painting. And the outcomes that are highlighted here were respect the scope and the goals of the projects. Another success story was a measure of the fading of the yellow tones, the yellow painting in the Van Gogh painting. Measurements were performed both by the group from Perugia and from Poland. In specific measurements, the users were Ella Hendricks and Koen Jansen from the Van Gogh Museum and the University of Antwerp. The focus of the access was the study of the alteration of the yellow paints and also the study of the composition and the thickness of the varnish layers. So measurements were performed both by the group of Costanza Migliani from Perugia, and the results from the provider of Perugia is the following. By means of the visible hyperspectral imaging, they were able to recognize the pigments and a few elements, whereas by means of the optical coherence tomography device developed by the Polish group, they were able to measure the stratigraphy of the painting in very small areas. And the thickness of the varnish layer was correlated also with FTIR measurements in order to recognize also the materials of the varnish. This is an example of cross-section obtained by means of the optical coherence tomography device. And this is the result of the FTIR measurement. Another example of OCT measurements, and as you can see, when there are more than one layer, FTIR measurements were done in order to provide information about the composition of the varnish layer. And again, also cleaning tests were performed by the restorator at the museum, and monitoring was performed by means of OCT device in order to measure the thickness reduction during cleaning. Why it is important, this Mahlab access? Because in the framework of the Charisma project, the same users asked for another access with more or less the same questions. But at that time, we didn't have the OCT device, so measurements were performed by means of XRF, FTIR, and so on, and only chemical information were obtained about the yellow, chrome yellow. I will not enter the detail of the chemistry, as I'm a physicist, just to show you the results obtained during the Charisma access. And this is why the measurements were considered very important, because the new access allowed to define the problems related to the fading of yellow colors. Another success story was the measurements on the Munch drawings that were studied in order to try to discover the process of the very famous painting. And the group from Perugia and also from Florence was there. And another success story with a scope of measuring the effect of fire that took place in 2014 on the sandstone walls in Macintosh building. And again, the result was pretty satisfying. And also a few examples of how Mahlab access can result in also very important publication that foster scientific excellence in heritage science. This was measurement done by means of our multispectral VIS near-infrared scanner that works from 400 nanometers up to 2.5 microns with one device. And it's again another example on the Memling painting. I'd like to show you this example because during the Hyperion project we had a request for an access in the Archaeological platform for the same paintings. So the results were obtained with those instruments, XRF, FTIR, UV visible spectroscopy, XRD and XRF, and multi near-infrared scanning. These are the instruments while measuring the painting, and a few results on a set of small areas in order to make pigment recognition. And again, the results with the pigment listed here. And here images at different wavelength in order to show the drawing, the underdrawing, and the sketches done by the artist. Here there is also a pentimento with a different position of the eyes and of the chin. And also the new instruments developed during Charisma project now are part of the Mahlab instruments that are the combined XRF and XRD instrument, the combined UV visible near-infrared absorption emission and time of decay, and then, okay, this one, and this one, and a tertiary system for bulk measurements, the optical coherence tomography device that was developed during the Charisma project, and a laser interferometry that is a digital holography speckle interferometer that is used to measure with high accuracy the surface of buildings, of paintings, of whatever, a mobile single-sided NMR, an XRF mapping, and finally a simulated infrared tomography system, again for measuring the presence, for instance, of cracks, of defects in wall paintings and so on. The very last example that was done during an access, national access on the painting Alchemy by Pollock, a very huge painting because it was something like 3.5 by 2.5 meters. Also the 3D survey of the painting was performed, and a digital model was realized, and after the digital model, a plastic model that now is exposed at the Guggenheim Museum in Venice. This is the museum, when also the results of all our measurements are visible on special TV, and a few results on the mapping of painting materials. This is Pollock when composing his artwork by dripping method. And this is the painting while it was restored at the Opificio delle Pietre Dure in Florence, and while measured by our visible near-infrared scanning device in Florence. And the result is the following. We can have display visible image by combining the 16 channel acquiring the visible region. We can select by using special masks the single hue, for instance the blue. This I cannot see it properly, perhaps it is violet, red, okay, yellow, I don't know what, and white. And again, we can, after selecting the single pigment, make false color images in order to recognize the pigment and discriminate ultramarine from the phthalo blue. And the group from Perugia made measurements in order to acquire also the spectra of the pigments. And again, in that part of the painting, we applied digital masks in order to select the yellow and the white color, and then recognize them by measuring with XRF and so on. We also made measurements before and after the cleaning procedure, and as you can see, there is a pretty huge difference between before and after cleaning. Our scanner is a non-contact device that can be applied also to very delicate paintings such as the ones from Pollock. We went also to Venice to measure all those paintings, and I think I have finished.
Thank you. So this, you continue?
Ah, okay.
You? So this is for the Mahlab, and
Can I have some water?
yes, of course. This is for the Mahlab, as Rafaela has mentioned. Apart from Fixed Lab and Mahlab, there are other platforms that are. There's a third platform already working in under Hyperion, which is ArcLab. It will be also explained by Rafaela, and we will finish. The last one will be the new platform that will be developed for IRIS, that will be the DigiLab that will be presented by Luca. I think it is.
Okay, thank you. So again, the FOR platform, and now I'm going to talk about the ArcLab platform. Very short story about heritage science. They started in 1807 with the La chimie appliquée aux arts, written by Jean Chaptal, and then the German chemist created the first lab within a museum in Berlin. In Italy, only in 1938, Cesare Brandi founded the Istituto Centrale per il Restauro in Rome, and in 1957 Paul Koreman created the Kikirpa, that is one of the ArcLab provider within Hyperion. Concerning the Italian situation, the Opificio delle Pietrature, that is the Italian provider of ArcLab, was founded in 1588 by the Grand Duke Ferdinando I, and the institute had to produce objects such as tabletops and panels with the so-called technique, the commesso fiorentino o commesso in pietratura. In 1932, Ugo Procacci founded the Restoration Lab at Uffizi, and only in 1967, soon after the Florentine flood, with Umberto Baldini, the Opificio was born. This is a slide that shows you the commesso fiorentino. These are very small pieces of marble that are glued together in order to make objects such as tables or paintings that look like a true painting. So restorers and artists were with the microscope or lenses in order to put together those very small pieces of marble. What is ArcLab? ArcLab is a facility that supplies data that are a variety of data ranging from images to micro cross-sections and so on, that are accessible to European scientists, curators, restorers, and so on. How does it work? The users has to go to the facility in order to access all those data. And the Shakespearean question could be, why moving to providers in the digital area? I mean, the most of our data are digital data that could be accessed in repository and so on. The main difference between ArcLab and DigiLab is that when a user goes to a provider, there is he or they can share expertise, whereas when you access data, you cannot share any expertise. The evolution of ArcLab is the following. It was born in the framework of the Charisma project, and then it evolved during the Hyperion project, and hopefully it will grow old during Hyperion HS, and finally in IRIS. At the beginning, we had 6 providers that were the British Museum, the National Gallery of London, the CDRMF, the Museo del Prado, Opificio delle Pietre Dure in Florence, and the RCE in Amsterdam. Presently, in the Hyperion project, we have 10 providers with the addition of the Prussian Cultural Heritage Foundation in Berlin, the Kikirpa in Brussels, the Instituto del Patrimonio Cultural de España in Madrid, I have missed an M, and the Center for Archaeological Studies and Conservation in Copenhagen. Hilde is the contact person for ArcLab in Hyperion. This is Hilde, obviously. And how you prepare a proposal. The best thing is to have a look to the website and have an idea of the archives and also the kind of data you can access. And then contact the contact person, the case is Hilde Leclerc, then write down your proposal. This is an example of the data you can access, and then you can see it is very improbable that you can have those data in a digital format. These are sort of microsamples put in a resin and that can be observed, for instance, by means of the optical microscope. Then you can access images of whatever kind, so visible, infrared, X-ray radiographies, and so on. You can access cross-sections, data, and also maps of elements, and so on. And also the original books describing the history of an artwork. When you fill the application, you have to contact the contact person in Leclerc or the coordination office of Hyperion, and then submit your proposal. The pipeline consists of sort of pre-screening, and then the proposal goes to a peer review panel. The peer review panel is completely independent from the Hyperion partners. Our panel now is established in Hyperion, and it is composed of those people. And when your proposal is accepted, you have to prepare the visit by contacting the providers, and all the flights and accommodation is paid by the provider. And after making dates, you can reach the provider. This is an example of provider user meeting at the Opificio delle Pietre Dure, where the provider is having a look to the X-ray radiography of a painting. And sometimes you can have some extra options, such as the user can give a short presentation, or can ask to see the artifact, or can ask to observe a cross-section, and so on. And when the users arrives at the provider, there is a general tour in order to visit the opificio, and then, for instance, the opificio or whatever provider is giving the access, and then the true access starts by having a look to all the data that are at the disposal. After that, you have to gather all your bills and receipts concerning, for instance, transportation, meals, and so on, because the user is going to be refunded. And then the administrative process starts. After the access, the user has to prepare a sort of project summary and fill a user satisfaction questionnaire, and that's it. A few examples also of success stories. In the case of the dome of Schleswig in northern Germany, the scope was assessing the causes of the yellowish gypsum efflorescence of the wall, and the provider was the Opificio delle Pietrature in Florence. This is an example of cross-sections at the optical microscope and at the SEM, scanning electron microscopes. And the outcome was that the nature of deterioration of wall paintings was discovered, and the yellowish patinas could be attributed to organic materials. Another success story was a study of the corrosion of inorganic objects, and here the provider was the British Museum and RCE. An example of an image, microscopic image, with the black spots on the bronze corresponding to the copper fluorescence, and another blue copper object. Or another success story, the scope was to study metal threads in Hispano-Islamic textile. The user was a student from the University of Sevilla, Spain, and the provider were IPCE, L'Opificio, Kikirpa, RCE, and SPK. And the results, again, these two microscope images showing the same stratigraphy in two different samples. The result of this study was very satisfactory. In fact, the providers had lots of greetings from the users. Another success story with the scope of studying the Champlain animals from Berlin museums. The provider was SPK. This is an example of a liturgical incense holder of the 19th century, and a microscope image showing that blue part that were studied and analyzed, and these are the intensity spectra, Raman spectra, that allowed to study the different materials used. This is another success story. We analyzed a painting by Manet in the Opificio, and then the access was performed at the C2RMF in France, where the original painting by Titian is present. And Manet, at the very beginning of his career, realized that copy of the master's artwork. So we went there. This is a portrait of Titian, and this is Manet. So we went to Paris, and we were given images acquired many years ago. So these are from Titian, and these are from Manet. And we performed the false color image using the same wavelength that probably was used to obtain that image in order to compare them. And we were given also a few spectra acquired only in the visible region of the pigment used by Titian. We made our measurements on the Manet painting, and we were able to discover that while Titian used lapis lazuli and azurite, Manet used cerulean and Prussian blue. The last success story is this one, no, perhaps not the last, but nearly last, because as I showed you before, the Memling paintings were accessed by means of Mahlab access, and the same user asked for having also Archaeological access in order to study the pigment used by the painting. So the provider was the National Gallery, and the user was interested in studying the gilding technique, and also to find a relation between the choice of the materials and the size of the panels, because Memlings used to paint very huge paintings. And this is an example of a cross section in London and in Antwerp, and the material look very similar. And finally, many paintings were analyzed by considering also very different dimensions of paintings. And I think the results are under examination. The very last example is this one. The scope was indirect loss wax casting and fusion welding, the study of those statues. And analysis by means of X-ray, tomography X-ray were performed in order to study all those objects. And I think that's it.
So thank you, Rafaela. We will finish this afternoon with the last platform, the DigiLab. Is the new one that will be implemented in Irish, and I think it is the last leg of the table. It will be a platform that is complementary to the other ones. I think we all agree that there's a need for this platform, and also in this field. And Luca will present how it is expected to work. That's one.
Yeah, no, that one. Go.
It's not in order.
Perfect.
So.
Hi again. It's my last talk today, I promise. So, well, as Rafaela was substituting Hilde, the clerk, in presenting the Arc I am substituting the data scientist who should have been here presenting DigiLab at the last moment. At the very last moment, he was stuck in Italy due to, let's say, administrative problems. So, I will discuss DigiLab. Speaking of DigiLab, as I said in Brazil, is like speaking of Neverland, because it's the platform that is not existing. So, it's a plan. It's a necessary plan that we had to take. In the beginning, we were thinking of solving the fact that the infrastructure, IRIS, will be a data producer in heritage science. As all the predecessors, initiatives, the projects you saw, are already produced digital data. But when we started the initiatives, the science was not open yet. And so practically speaking, the rule was that data are owned by the users. Frankly, this rule is still there, but now the complication is that the data are owned by the users, but the users need to open the data. So there's a contradiction, apparent contradiction in what is happening in Europe. There is the fair concept that science data needs to be findable, accessible, interoperable, and reusable. This is the mantra of data science in Europe for which Europe is also building a very nice initiative, the European Open Science Cloud. So to be compliant with the rules of creating with public projects digital data by science, actually, and the rule is everything that is paid by public money needs to be public access. Needs to be, and this is why we, in the beginning, we thought of using the services of another infrastructure in Europe, the real digital infrastructure, which is still there, and it's called Daria. And I worked for Daria 5 years. I was the national coordinator of Italy. And I asked them, look, we will be IRIS, we will produce digital data, we need someone to take care of this. And then I started negotiating with Daria, but then we soon realized that the Daria infrastructure was capable, and is still capable, of handling data in the form of publications, in the form of digital books, in the form of images, audiovisuals. When it's coming to, let's say, three-dimensional data sets and on spectral data, tomographic cubes, okay, let's forget about that. And so is why we finally decided to have our own digital platform, which, considering everything, will be actually a full European digital infrastructure contained inside IRIS, increasing the complexity of setting up this infrastructure, because it's a collection of separate, you see, infrastructure inside. And DigiLab is the platform that we started to plan for, because we need a platform such as DigiLab to establish a common infrastructure of open data and services. And we expect this platform to have lots of users. And we have to manage to handle and to make findable, accessible, interoperable, and reusable this kind of data, which is not about publication, it's more about real data sets in heritage science. Data sets obtained by measurement. Each of the other platforms in IRIS will produce digital data. Even Archaeological will produce digital data, because they will reanalyze data, existing data. They will probably digitize archives sooner or later. And when archives and content of archives in Archaeological will be digitized, they will end up in DigiLab as service to the researchers. So, what we are trying to do? We are trying to collect solutions that are already around, because there are other projects, there are other infrastructures in Europe, and this is a short list of those. In Daria, as I already said, Daria is still a collaborator of IRIS. It's actually one of the partners of the preparatory phase. We know that they cannot handle these data sets, but they can help us make in some sense with the use of digital data. As well, the cluster Parthenos, which is going to finish in October, like Hyperion. It has been a 4 years cluster, mostly devoted to development of solutions for digital data in humanities and also in heritage. We have also a cooperation with the Ariadne community, which is another integrating initiative in Europe, which succeeded in opening a registry of archaeological data sets of any nature, publication data and also scientific data. So Ariadne is in between Daria and IRIS, let's say. Now Ariadne Plus has been approved, so we continue the relationship with the digital archaeology integrating activity in Europe. And then finally next year, the cluster, Social Science and Humanities cluster, which this horrible acronym, SHOCK, which will be the cluster for promoting the use of the European Open Science Cloud in our domain, that is for humanities and heritage. So in this cluster, some new researches for helping to put the digital data in the cloud. So there are a lot of movements, but we start from a reality, a sad reality, that in our field data are open by definition, but actually restricted by necessity. And when you go speaking to museums people, the need to open digital data in heritage, they got like this, scared. But actually there's nothing to do, at least in Europe, the law is that one. And so you imagine which kind of IPR management we need to have. It's so complex that we renounced for the moment to manage that and to have a different approach. So like Ariadne, we will create registries. registries of where the data are. As well, we will create registries of where the tools for using the data are in the big internet. Then we will connect these, but of course we will not provide the users with the data sets because of the property. But the researcher will know about this data exists, and probably she will be able to contact the owner of the data and the last mile approach, and come to an agreement for using this data in his or her work. So the data repositories will not initially be part of Digilab because they will be local. The data will remain where they are. How we make these data repositories findable, which is the first requisite, and this is the discussion of this morning. We need to create metadating system. And to create metadating system, we need to solve a lot of problems. We can suppose that the object of heritage is already defined in the digital world. That is the case, let's say, with famous objects, with objects already inside national catalogs that are already digital, so you see. But we say, in principle, in a certain period of time, all heritage data or heritage objects will have their digital description in the digital world, let's say. This is not within our reach, of course, because listing and describing the actual heritage objects is not a task for IRIS, it's a task for the Ministries of Culture, for the institution which are keeping the catalogs all over the world. Let's suppose that somewhere that object exists in the digital world and they have clear identifier. Maybe, hopefully, it will have a persistent identifier, and maybe in the future it will be a real digital object as that is going to define at least at the European level. Well, what will be needed to metadata our measurements? It is having a description of the protocol with everything, including the calibration of the instruments, probably, because it's relevant for future reuse of the data sets. If we have to open the data sets, the data sets needs to be usable. And if you put on internet a measurement without describing how you did the measurement, so protocols, etc. So you see that we will need to agree on protocols, and we, in a certain sense, will need to digitize protocols in order to be linked. I don't want to describe every time that I do a measurement the protocol inside the data. I prefer to say, I used that protocol, and so the protocol is described elsewhere. So that is why we need to agree over protocols and to create repositories for standard protocols, but they can be more than one. It's important that they are coherent, consistent in a scientific way, and described in open form somewhere. So we describe the measurement, we say we use that protocol, we did the measurement this and that, and we measured that object linking to the objects described elsewhere. So you see the complexity of this system which needed to be created, but for the future and for using the digital means to do research, there's no way out of this approach. So in the beginning, Digilab will just be a registry of data and a registry of tools, a matchmaking between the tools that you can use and the data and where you can find the data. Developing things, of course, we will start IRIS. We will start creating IRIS digital data sets. We will contract with IRIS users about the fact that after a few initial embargo, we define 1 year, 2 years, we will contract with the user, the data will be available, and so Digilab will start publishing their own data sets, data acquired by the infrastructure. That is the way forward. And so you see that we are creating a virtual research environment which will be probably based in the cloud, which will evolve in a digital platform. And the digital platform has this very special characteristic in IRIS. It is not a physical access platform. It's a remote, it's a virtual access platform. So it can be used from everywhere. And this is the reason why we see that a true international cooperation will be really possible using the digital platform. In a certain sense, we can have a starting point this way. We are trying to open the heritage data in Europe and create this platform using European providers through the in-kind process. Facilities in Europe will give dataset services, software, in kind to the platform, and the platform will allow this to be used from outside Europe. But of course, to use digital resources, you enter the realm of privileges. In the digital world, you can have different level of privileges to access things. And so why you can be interested in having the partnership on an equal level. You open your data here in Mexico, there in Brazil. You provide your tools with the same, and you become, in this sense, a real provider of the infrastructure on your side. And being a real provider of the infrastructure, either in a global RIS, in a global future infrastructure, or through a direct bilateral agreement with the RIS, you can be allowed to have an equal use of these resources. European researchers can use your resources, you can use European resources. This is the base of real international cooperation on the fact that we are creating this digital platform. So when, it's a long process because the things to be solved are so many, but right from the start, we have people working on this, we have projects working on this, we will have more projects to work on this. What we are starting is a working group, and I already invited people from the US, data experts, or volunteers from the US and from Brazil, to take part in the discussion working groups that we are creating for IRIS, because we have so many things to discuss, to come to agreements that can be satisfactory for the future. And we find very stupid to limit the discussion to Europe, because finding an agreement across Europe makes no sense for this platform, because we want we want to cooperate even outside. So probably the best place to discuss this kind of thing is the International Forum of Research Data Alliance, which could offer also the environment for interest groups and working groups over DigiLab to be created and to have visibility even outside the heritage science group. So this is more or less where we are pointing, but to conclude, I invite even you to select 1, 2, 3 data experts in your heritage group and to connect these people with the working group that we are creating for discussing DigiLab within IRIS. Well, that's all on my side. Thank you.
So we have finished our program of presentations for this afternoon. Thank you very much to all of you who have presented. Now we have time for discussion, for open discussion or for questions. So is there any question or any comment from anybody to any of the presentations in this afternoon? No.
It's better that I make it. No, considering the wealth of instruments, techniques that has been presented throughout the afternoon, I say that instruments are there, and that is good. Now, for a good cooperation, we need people and ideas. But the instruments and the technologies are there, and I think that we can really have a peer-to-peer cooperation with the system you have here in Mexico without any suggestion that things are better in Europe, because they are not. And so the base of this cooperation, I think, will be to share problems in heritage science, as we have capacities. And I think this should be the real point, the real key point in keeping this collaboration open. You did an excellent work in these 3 years, José Luis.
I think it's the most important, for example, for Archaeological data or general data geometry. We collaborate with a database that is in Europe nicely is named, and all the papers that are published with the results are of that database, and we consult because we use this data to did the models of the Earth's magnetic field for all the times, and then everybody cooperate. Then I think it's another way to cooperate with data, for example, of the paintings or the different minerals used by one artist or something like this. But the other problem is the problem that was talking about Luis in the morning, the problem of different instruments than then, for example, we is accustomed to do intercalibration in all the instruments with samples, model samples, that everybody at the same time, but I think it's like 1 or 2 months, they send the samples or the laboratories first ask if you want to collaborate. Then when you ask, you receive the sample, and in 1 month you send your results to one person, and that person did the exercise to compare all the results. That is another matter, very important to talk about the same. And I think this is important as well. Thanks.
I think it is something that is, as you said, it is something that is important. It's something that can be done without too much resources. So, which is probably one topic that is very interesting for starting collaboration. Of course, sending samples across the Atlantic is more expensive, but in any case, it is much cheaper than sending instruments or people. So this is probably another topic that can be interesting. Any comment, Luis? Or?
Yes, I would like to comment that we are just beginning with the databases in our network, and we began with the Obsidian database, and has been a very interesting exercise. And as you mentioned, laboratories that provide data have the right to take the data from the database. This is an exchange of information that is going to be easy, but the problem is going to be when the data is provided by the Archaeological project. Meanwhile, the exchange is between the laboratories, and they are mostly geological samples. There is no problem to share and to be part of the database. But the problem is going to arise when the data come from the archaeological projects, because there is this kind of property of the well, we have to think about this. But one interesting thing is that when the data, we are beginning with this data, but if you are ahead of that with some specific ideas of how to handle all this information, we want to go behind you to be in the same tuning and avoid to finish with our database and said, well, it was not the format and we have to redo it again, all over again. So something like this could be very helpful in the future.
I will not say that we are ahead, because in the digital world there are so many solutions fragmented that we want also Digilab to be kind of a map for orient people and researchers in this world, because so many databases around, so many tools for analyzing data in, unfortunately, so many different formats. If you think to the number of different formats described for the GIS, or even from the building information model, for the beams, each institution seems to have their preferential way of doing this. Clearly, this situation is not sustainable, because we cannot use the data each other if imagine each of us is using a different word processor. It would be total madness. So we are not ahead. We are in a transitional phase. We have what pushes us is this new policy in Europe since a few years, which we need to open the data. But I think this kind of policy is not just European, because coming back from San Francisco conference on digital heritage, also in US, that's the feeling that they need to adopt a kind of policy this way. And about archaeologists, at least Ariadne did a good work, preliminary work with archaeologists in Europe, because they are willing to share, and the number of partners of the new project, Ariadne, is more than 40 partners sharing archaeological data. So there are hopes.
Yeah, I think this is, regarding the data, this it's my feeling. Probably it is not something official. I feel that we are in a kind of transition phase regarding data. There are policies that are pushing towards sharing data. Now, everybody has more or less accepted quite well the open access to publications. Of course, it is not working perfectly, but in the ideas of the researchers, it is something that is more or less well accepted. And it sounds very reasonable. As you said, if we are doing this with public money, the result, the outcomes of our research should be public. Of course, data is a step further. I'm sure in some years there will be some systems, for instance, to give credit to data. This is something that is new. Now we are giving credit to publications. Everybody knows that you mention something that has been done before you mention the publications. Of course, this needs some kind of technical development to be able to trace back the origin of the data, but I'm sure in some years we will see how we are citing papers, but we are also citing data that we have taken to do this research. Of course, there will be a lot of exceptions or embargo periods. These kind of things should be implemented I personally think this is something that needs to happen. We cannot really keep on doing things as are being done now, that a lot of data is published, is obtained, but that data, in the case, for instance, of archaeological excavations, remain in the drawer of the researcher. Sometimes they are published early, sometimes they are published many years later, and sometimes they are never published and end up in the drawer covered with a layer of dust. And those data are very valuable and have been obtained in many cases with public data, in most cases during an excavation that is destructive, so cannot be redone again. So we have to develop some ways of being able to use that data for the benefit of everybody, not only for the benefit of the researcher that has obtained that. But that's my personal view. I think this is something that we will see. A comment?
In Mexico, we have the same problem with this research that is made with the public resources. We are obliged to open all the data to the public, to the persons that are requesting this information. So the idea to have this working group, I think, is very good. We need to think how we will use this data, because I think this is perhaps the first idea about how we can manage all this information. But it's different to have a data of obsidians on paintings. As you say, the amount of information, the kind of files is a problem. We had been working since almost the beginning of the lab with some ideas about how to handle all this data, but we are stopped because certain time it's not possible to continue with the first idea. So I think we may have some working group, would be a good idea, of some people that may join the meetings to know how we can handle, because we don't want to make the work twice or 3 times. This is something that we don't want to invest resources unless we have a clear idea about how to handle this problem. So I also consider that the proposals to start the collaboration, besides the training and so on, is to think about these challenging problems that we have, and that request this new development of instrumentation that you saw in the OCT, for instance, is very interesting, or the terahertz imaging that has been improved very quickly, are methods that perhaps we can think about that can be solve some problems that we have here in Mexico. So I think we can prepare some kind of problems that could be that need some more technology or experience or development that we can do together. This is something that we can work in the next month to think about this person that may join this working group. But I don't know if you have a specific working group for cultural heritage. Because, as I said, this idea to be part of this European project about databases is good, but I don't know if they have this kind of complexity of imaging, data, spectra, and so on.
The situation in Europe in Europe is that we don't have so many experts in digital things. You see, many institutions, but the digital literacy, we say, of this scientific community compared to others is slow. With the other complication that parts of the community, they know very well digital use because all the disciplinary parts, physicists, chemists, they use digital. And each of these sub-communities use their own tools in the digital world, so adding to the confusion. So first, in a certain sense, we are trying to list a group of digital experts that they want to work together just to define the implementation lines of Digilab, because we know Digilab should be this, but then we need detailed implementation lines and problems to be affronted one by one, step by step, until we come to solutions. In this sense, we probably will have the need of having thematic working groups, one for bidimensional images, one for tomographic cubes, one for that is that. We try to approach this problem in voluntary basis in groups in Europe recently, and the idea was to connect a data expert, one of the ICT side, with a measurement expert, telling the data expert, look, the measurement we do, the workflow of the measurement we do is this one. In this sense, there has been an interesting experiment which has been done at the plenary meeting of the Research Data Alliance, I think it was Montreal, by John Henry Scott of the NIST. He called all the microscope producers plus other people, and he tried to start a group in Research Data Alliance to make an homogeneous use of microscopic data. This is also of interest for us, but you imagine that for us each kind of metrologic aspect should be tackled and solved if we want a real cooperation and if we want to produce data sets that are useful because are really interoperable. But if we don't start the discussion, we will end up with separate solutions, one for Mexico, one for United States, one from Brazil, one from Europe. In a few years, we will have new silos, new standards, each one its own standard. So that is why I think maybe worth to have a more complex situation, but involving many different countries in the world. So if we come to maybe simpler solution, but they will be global. If we solve, for instance, which would be the use of the standard for image, do we want to use AAAF? Do we want to use Mirador as a tool in three-dimensional as well? Do we want to use 3D Hop, for instance? Easy solution, not very aggressive, but valid throughout the world. Solution over which we can build. It's a long process. The referee, the American referee about the IRIS project told us, magnificent initiative, it will take 20 to 40 years to be implemented. So you see.
Yes, because the technology will change, so afterwards we will see.
The infrastructure will follow.
Yeah. Okay, so let's think about this. Tomorrow we will have some colleague from Mexico that has been working with databases, and he has some idea that perhaps could be interesting to listen about how to handle this problem. And the other interesting thing that I found here is the Arc labs, or the archive management, because in the groups we don't have really samples or archives, these kinds of archives, because in our laboratory we have non-invasive methods, so we have very few samples, but we have reference materials that can be approached about this idea, or to have an open access to the collections of references. But there are other colleagues that have samples, and I think they have a similar approach to have a database and order all the information, and if someone needs the information can approach, and they have to sign only some agreement about the use of the information. And I think it's the way that it's being working in the Art History Institute, where they have also the collection for mural painting, pre-Hispanic mural painting and other projects, and they have some samples and some material related to imaging, mainly photographs and other information. So perhaps there is some information, and there is also another approach that has been done by our colleagues of the Center of Conservation, the National Center of Conservation, because they made a collection of all the samples that were lost, that were on the table, on the drawer, and were forgotten. And they have this collection of samples that they can borrow for research, to test methods and to do testing of different techniques. This is also it's cultural heritage. We don't know where it's coming from, but for research is good. We can apply methods. So this is also interesting. If we have a collection of samples of artifacts that are lost and nobody wants to have that, it happens. You know, in Mexico, when after all the archaeological excavation, there is a lot of material, ceramic material, that has to be kept in some special places, and they stay there for almost all time, and nobody wants to do anything with that. So, but it's a source of information that can be used. So this is the case of these archives that are there, and nobody wants to use it sometimes. Okay.
Make comment on this on ArcLab. ArcLab is not only about the samples; it is also about the data that has been obtained. You know, in Hyperion, the ArcLab providers are museums, are conservation institutions, so are institutions that have obtained their own scientific analysis using their methods and their techniques, using their samples. Usually this information is obtained only for, let's say, in-house use. It is only for their use. And there is that is a huge amount of very valuable scientific information that is usually it is not accessible. It is not at least easily accessible So having these collections of data, of samples and scientific data that is mostly unpublished, it is not known by the scientific community, and opening these collections to researchers is a very interesting way of accessing already existing data that you cannot access in other way. You can obtain a very valuable information just by going to these institutions and looking at the archives and discussing. Also by discussing with the researchers or the scientists or the conservators or curators that are there. And we also know from the experience of the ArcLab providers that it is a two-way benefit. It is not only for the people accessing the infrastructure. These people, these researchers that come into the infrastructure to access some data have also some experience and background, and by means of this interaction, this is something that Rafaela has mentioned, one of the most valuable things of ArcLab is the interaction of the researchers coming from outside and the researchers from the institution providing this access. And this interaction also benefits the institution opening the data. So it is not just saying, okay, I am opening up my archives for the benefits of others. I am also benefiting, having some profit from that. And this is what the institutions, for instance, the IPCE of the Prado Museum, when talking with the scientists working there, they say, okay, it is very interesting because you know your data, but when somebody from outside knows of this data and discuss your data in view of their experience and their knowledge or the data they have from outside, gives you a new view of your data, and it is also helpful to learn from your own data. So it is also some interesting way of interacting with these cultural institutions, these museums or conservation institutions. They are not only coming to, let's say, the scientists to the scientific facilities as users, but they are also participating in this infrastructure as access providers. It makes a more equal, more balanced participation of these two kind of institutions, and it can also benefit this. This is something we were discussing, I don't know, this morning with Sandra, no, with Isabel. This is also a way of bridging this gap between the cultural institution and the scientific institution, the academia and the museums, and to also to improve the trust and the confidence between these two worlds, which is, I think, it is one of the big challenges we have in this field.
Do you want to comment something, Santa? No. No.
Just about our sample collection, our sharing of the samples and the information, as you said. It has been interesting because since we are at the university, some theses have been worked with just the data, no, without going again to the just analyzing different sets of data from art history point of view, no, the materials, results of some specific scientific research, or from a broad range of, for example, like the palette of the colonial painter, or I don't know, no. And on the other side, I think in Mexico would be interesting for the cultural, the institutions that have the conservation, no, that have the objects in their hands. They also have all all the documentation on the conservation approach that I think it's very important. No, also, well, in our institute, what has happened is that images of objects that had been lost, are important because sometimes as the earthquakes or any other catastrophe, may happen, and just the image is a quite interesting thing. But in the thing about a database, I don't think we do have in Mexico still, like a good digital scientist involved, I think probably at the INA, they do have like more, because they have a bigger problem that it's like doing all the cataloging of all the cultural heritage, as you said. They do have someone more, but when we seated with all the national lab, to see all the kind of objects we had, it was really a mess, to see, just to give a list, it was like forever, I think we still are doing like the list of kind of objects and kind of different platforms we use to analyze data, and so I think it's a complex situation, but probably we need to involve someone at the university. I don't know, I don't know. Don't have the answer.
Tom, what's the experience of the Getty about all this? Because I think you have also some point of view about these problems.
Yeah, but no nice answer for you. So the GCI. So I'll step back. There's actually a brand new program just established at the Getty called Getty Digital, and so this is a fifth program, in addition to the Conservation Institute, the Research Institute, the Museum, and the Foundation. So it's a fifth of equal status in recognition of the enormous needs of the field in digital management and digital everything. And we're really struggling to figure out who goes where, because of course digital is all over everything. Specifically, and I think at previous Hyperion meetings, we have been trying to develop some sort of open source software for data management, data integration and management of scientific research. The project has a name called DISCO. It's been running for 3 years, and really there's still nothing to show. It's just when you start to look at all the data coming from the different experimental and analytical techniques and try to find a platform that can import these things, compare them, search for them, all those things that Luke was talking about. It's really tough. So we are trying, and this is not the multi-million-dollar sort of project. This is working with someone who's used to working on open source software just to get us started, and it's taking a very, very long. Every time I come to a meeting like this, people often say, "What's up with Disco?" And no one did this time, but I've just offered up that information. But it's taking a long, long time. And maybe this 20 to 40 year thing is realistic. Who knows? So that bit. What else were you talking about? You were talking about so reference materials, and I mean, it's one of the things. We have a very large reference material at the GCI, reference collection at the GCI. It's about 14,000 materials, and it's all catalogued in a FileMaker Pro database. But we kill ourselves thinking about how we make better use of this collection. You know, people can come. You can come and look at the database. You can take samples, but it's a very long-winded process for people to travel, etc. But recently, in the last 6 months, there's been a number of institutions, mainly the US, but also some in Europe, who've just tried to get together to think about if there is a better way. This is probably 8 to 10, collections, so fairly small number, to see whether these can be integrated together. We're very interested in trying to add, data to some of our collections. So when you just add FDI or Spectra or XRF data, or things you can actually push out to the field without having the actual material itself as being the only thing. But again, this is a huge project. I mean, 14,000 samples to do analysis on, and interpret and make sure it's accurate and make sure the material is what it says it is. But it's recognised, I think, by us that we have to play a role in this somehow. So no magic help yet, but we're absolutely thinking about this in the same way that you all are.
I think there are some ideas interesting, but we need to start with something. Yeah.
For example, another thing that we are thinking. For example, in the museum, well, now there is one research that he is going to repeat the records in the old seismograms with the new seismogram taking the same records to reinterpret the old records. And then I was thinking this was the same, for example, with the resolution of the old spectrometers, or many information that has to be inside many archives, that maybe we can choose one, only one lab, and try to do that. A lot of work.
Yeah. Okay. I don't know if you want to share something else. I think we had discussed enough, just to start to think about how we can propose something that could be interesting for both teams. Yes. I don't know if there is something else. I think that we
should
close.
We have tomorrow as the last panel of tomorrow, as we did in Brazil, and we use the last discussion to literally write a list of action items. So I think after seeing everything in this 1 day and a half, tomorrow afternoon we can come to, as we did in Belo Horizonte, write down an action list.
Yes.
Because we don't want to cooperate in theory. We would like to start cooperation in practice. And so we have the night to think of it, and the remaining of tomorrow. We already put several proposals on the table, so we can see what it can be really and quickly done, and within the economic conditions that we have on both sides. So the resources that are already there.
Okay. Yes, I agree. We have already an organization. We have ideas, and
we have a lot of things,
think about,
actually.
Yes.
So, and most of that, we have the will to cooperate. That's the most important thing over all the organization that we represent.
Okay. So then we want to thank you again to all the speakers and people that have been here in these presentations. And I think it has been a very interesting workshop, and tomorrow will be also very interesting as well. Okay. Thank you.
Start at 9 tomorrow?
We start at 9.
Yeah,
yes.
perfect.
Yeah.
So now we know where the institute is, so we will arrive on time.
Okay. Thank you very much. Have a good afternoon.